Hi everybody and welcome back. In this notebook we will build the UNet to tackle the task of Atrium-Segmentation. Only one import is necessary, which is PyTorch. The idea behind a UNet is the encoder-decoder architecture with additional skip connections on every level. The encoder reduces the size of the feature maps by using down-convolutional layers, whereas the decoder reconstructs a mask of input shape over several layers by upsampling. Additionally, skip connections allow a direct information flow from the encoder to the decoder on all intermediate levels of the UNet. This allows for a high quality of the produced mask and simplifies the training process. At first, we define a single convolution block. We use two convolutions between each down or up convolution step. Let us create a class doubleconv for this, which inherits from torch.nn.module. We define the initialization function, which accepts self, the number of in channels for each convolution, and the number of out channels. Above all, we call the parent constructor. Next, we define a sequential object that contains two convolutions, each followed by the ReLo activation function. Let us store this sequential object in a variable called self.step and now call torch.nn.sequential, to which we pass at first the first convolution. The initial convolution has in channels, and out channels. We use a kernel size of 3 and Z padding to 1. This makes sure that the convolution doesn't reduce the shape of our input. Next, we add the rectified linear unit. After that, we add the second convolution, which has out channels, in channels, and also out channels. Again, we use a kernel size of 3 and padding of 1. Last but not least, we add the second rectified linear unit. Alright, we successfully defined our double convolution. Last but not least, we have to define the forward function to implement the actual logic. It simply returns the output returned from calling self.step on our input variable x. Cool, we just defined the most important block of our UNet. Using the previously defined doubleconv module, we can now easily implement the UNet by combining doubleconv with max pooling for encoder layers and doubleconv paired with upsampling for the decoder layers. Let's define the UNet. Of course, as this is a PyTorch model, it also needs to inherit from torch.nn.module. We will build a UNet with 3 down and 3 up convolutions, respectively. Let's define the initialization function and directly call the parent constructor. In this lecture, we will hardcode the model, but if you want, you can of course also pass all parameters to the initialization function. Alright, let us begin to define the down convolutions. We create a variable called self.layer1, to which we assign a double convolution block that has 1 input channel and 64 output channels. As our single slices have only one channel, we need to pass the 1 here. The 64 out channels are free to choose. We store the second down convolutional block in self.layer2, which has 64 input channels, because our previous block had 64 output channels, and 128 output channels. The third block needs 128 input channels and we wanted to have 256 output channels. Last but not least, block number 4 has 256 input channels and 512 output channels. Alright, we successfully defined the encoder of our UNet. Now it is time to tackle the decoder. The first layer of our decoder, self.layer5, should have, of course, 512 in channels. However, since we are using skip connections, the output from layer 3, which has 256 channels, is directly forwarded to the current layer 5. Accordingly, we have 512 plus 256 input channels. Additionally, we wanted to have 256 output channels. Let's define the next layer, self.layer6. Please take a second and think about the in channels this layer should have. As layer 5 had 256 output channels, it definitely needs to have 256. However, the output of the second layer had 128 channels. Therefore, we need to add those 128 channels to 256. 128 is also the number of out channels we want this layer to have. Layer 7 will have 128 plus 64 input channels and 64 output channels. Last but not least, we define our output layer, layer 8, to which we assign a new convolution, which has, of course, 64 input channels, 1 output channel, and additionally a kernel size of 1. This layer is responsible to produce the final segmentation. We can furthermore define a maxpool variable which stores the torch.nn.maxpool2d layer to save us some typing. As we want to reduce the shape of the features by 50% each time we call maxpool, we pass 2 to its constructor. Perfect! We successfully defined all individual layers. Now we have to implement the forward function to define the forward pass. We can feed our input variable x through each of the 8 layers and store the result in a variable. To calculate the output of the first layer, we call self.layer1 on our input variable x. This result is stored in x1. We can define a variable called x1m, which stores the result produced by the max pooling layer. Alright, x1m now contains the output of the first encoder block. In order to get the output of the second block, we define a variable called x2 and call self.layer2 on x1m. Additionally, we define x2m to store the result of the max pooling operation. Let us copy those 2 lines to calculate the output of the third layer or block. We simply replace x2 by x3, x1m by x2m, and x2m by x3m. Make sure that you don't forget to replace layer 2 by layer 3. Now, after 3 down convolutional blocks, we calculate the output of the intermediate layer, layer 4. We define x4, which takes the result when calling self.layer4 on x3m. This completes our encoder. In the decoder, we perform 3 steps. At first, we upsample the current feature map with a factor of 2. Next, we implement the skip connection by concatenating the upsampled features from the decoder with the matching ones from the encoder. Last but not least, we compute the output of the corresponding decoder layer based on the concatenated input. So we at first define our variable x5 and then call torch.nn.upsample, to which we pass at first the scale factor of 2 and next the mode, which equals to by linear. We directly feed the output of the previous layer to this class, in this case x4. After that, we override x5 with the result of torch.cat, which accepts the list of the two features we want to concatenate. In our case, it is x5 and x3. Additionally, we pass dim equals to 1 to concatenate along the channel dimension. Last but not least, we override x5 once more with the result returned when calling self.layer5 on our concatenated features. We can now copy those 3 lines 2 times to define the second and third decoder blocks. In the second block, we replace x5 by x6, self.layer5 by self.layer6, x3 by x2, and also x4 by x5. In the third layer, we replace x5 by x7, self.layer5 by self.layer7, x3 by x1, and last but not least, x4 by x6. We are now ready to compute the final segmentation. Let's define a variable called ret for return, which stores the result produced when calling self.layer8 on x7. Returning ret finally completes our UNet. Awesome! You just coded a UNet from scratch. Great job! The last task we should address in this lecture is the validation of our implementation. To do so, we at first create an instance of our model. Great, that worked. Next, we define a random input by using torch.randn, to which we pass the shape the returned tensor should have. Let's use the shape of our cardiac MRI slices. At first we pass 1 for the batch size, next 1 for the channel dimension, followed by 256 times 256. We can now compute the prediction or output based on our random input by calling model on our random input. Let's write an additional assert statement which makes sure that the shape of our output is equal to a torch.size object of shape 1 times 256 squared. Perfect! Our model works. We should copy our UNet together with the doubleconf class to a separate Python file to allow importing it in the training notebook. We of course need to import torch, copy doubleconf, and last but not least, our UNet. Let's call this file model.py. Now we are ready to face the final lecture of this project, namely the implementation of the training routine. Thanks!